In this video, we're going to take a look at the IB bullet point 10.5.1, which asks us to describe using equations the substitution reactions of halogenoalkanes with sodium hydroxide. Previously, we've learned to make halogenoalkanes through the substitution reaction of alkanes with halogens. This chemical type has many functions. One of them is that it's a good starting material for a number of compounds, including alcohols. In this case, we're going to take a look at this reaction where we're going to be considering the process of it reacting with hydroxides. And hydroxides in this case, because they have this pair of electrons here, act as what is known as a nucleophile. Now, a nucleophile is a substance that is going to be attracted to a positive charge. If we take a look at this halogenoalkane, bromine, because it's a halogen and because it's more electronegative, tends to draw electrons toward it, generating what we call a partial negative charge. That partial negative charge means that this bond becomes polarized and the carbon becomes partially positive. The term nucleus, nucleophile, derives from the fact that this carbon has a positive charge much like the nucleus of an atom. These electrons are attracted to this carbon, and therefore we say that this hydroxide ion here becomes what's known as a nucleophile. In the process of the reaction, the electrons that are associated with the oxygen are going to form a bond between the oxygen and the carbon, and they're going to create ultimately a new product. And that new product, we see down here at the bottom, is an alcohol. So as we begin here with a primary halogenoalkane, we react it with this hydroxide, which is going to form a bond here with the carbon. The end result is going to be a primary alcohol. The other product that's generated is a bromide ion, which means that at some point in time, this bromine, this bond must break, and it must generate an ion here. And when that bond breaks, this bond is going to rupture in such a way that those electrons are going to become part of that bond. So what we're asked to do here is to talk about the process by which this occurs. And the process by which a reaction occurs is known as the mechanism. We want to be able to discover what the mechanism is by taking a look at what's known as kinetics. Kinetics is the study of chemical reactions, and by looking very carefully at that reaction, we can determine which of these factors, the halogenoalkane or the hydroxide ion, or both, impact the rate of reaction. By knowing that, we can start to tell the story about the reaction. So first we must do the experiment. When we go in and we study this reaction here, this overall reaction, it turns out that experimentally, the rate of the reaction is determined by a rate constant K, which is always true of kinetics reactions. There's some constant that connects the rate to the concentrations. Experimentally, it's found out that one of the factors that becomes important is the hydroxide ion, the OH minus. So we find that in that case, that our hydroxide over here, one of the factors that shows up in the rate. The other one is the halogenoalkane. So what that means to us is that both of them are involved in the process. Somehow there is a collision between the two, and in that collision yields the ultimate reaction. So what we say here is that this reaction is first order in hydroxide, because if I double the hydroxide concentration, I double the rate. It also turns out experimentally that it is first order in the halogenoalkane. If it's first order in each of these reactants, we say that this is second order overall. So this is a second order reaction. Nice chance to review kinetics. It's a second order. This reaction that's going on here, because it's a saturated hydrocarbon, and this element, this leaving group, is being replaced, we say that this reaction is a substitution reaction. What we're trying to do at this point is explain why the name of this mechanism has become what it is. So it's a second order substitution, and this hydroxide group, we've already said, is a nucleophile. Nucleophile because it's going to be attracted to the partially positive charge on the carbon. The result is that we end up calling this reaction a S substitution N nucleophilic reaction of the second order. So it's called an SN2 mechanism. So that's the terminology we're going to use to apply to this. This is occurring with a primary halogenoalkane and making a primary alcohol. So what we now wish to be able to do is go in. We know the mechanism roughly because we know the rate law. The mechanism must be consistent with this process. And what that means is that the slow step of the reaction must depend on the OH minus, and it must depend on the halogenoalkane. So we're going to attempt to go in here now and take a look step by step at what's taking place. So as we come in here and take a look at this process, we're going to be using a technique known as curly arrows. And curly arrows allow us to look very closely at the exact process for what's going on. We're going to try to show a little bit of the geometry here. Remember that this is two-dimensional. All of these bonds are tetrahedral. So we're going to think about the idea that this pair of electrons, I'm going to show that with a curly arrow, is going to come in and is going to form a bond with the carbon. Notice that the bromide hasn't left. It means that both of these species are important in the reaction at this stage. So we end up having this process here where we're going to end up with a compound which is going to be looking a little bit complicated. So in this first step here, step 1 of the mechanism, this carbon, we'll focus on it out here at the end, will have the OH. It will still have the bromide. It will still have the other two H's. And the terms we're going to give to these, we're going to call this the leaving group, because ultimately it will go away. And here's a nucleophile. Now the molecule hasn't fallen apart. We've still got our other two carbons sitting out here with the H's. The focal point is the reaction site. Okay. So in step 1, this is going to occur. Ultimately, this leaving group is going to leave. And down here, so we can think about another arrow, it's going to form the alcohol, because this is the nucleophile, and the bromide ion is going to have gone away. But here we want to focus back again at this point. This curly arrow says that those electrons that were on the hydroxide now reside in this bond that's here. This is step 1. This is the rate determining step. It is the slow step. And again, that means that it has to be consistent with the rate law. So notice that hydroxide ion and the halogen alkane both show up in here. So what takes place in the next stage of this reaction? We're going to find that here that we're going to take our intermediate piece, and we'll talk about that language in a second. So we had our carbons. Is the H, the OH, the Br, the H, these pieces that are here. And we're going to talk about the idea that this structure doesn't show up as a reactant or a product. So we kind of bracket it out here because it's sort of an imaginary species. We don't know exactly if it's there. And we say that it's an intermediate, neither a reactant or product. In some language they call it also a transition state. Transition state. Now, in this case, the next step, step 2, we can call it step 2, this material is going to break down. It's going to make the bromide ion. That's one thing, in a fast step. Fast and slow are relative terms. It just means it's going to occur much more rapidly than the first step. What has to happen here is this bond with a curly arrow. A little arrow here, and it's going to make a pair of electrons. The leftover material, the one we really care about, is our substance back down here now to having 4 bonds on the carbon. And this becomes the alcohol. The alcohol is a primary alcohol. We call it a primary alcohol because it has these 2 H's here sitting on the same one. Specifically, it is a 3-carbon alcohol, right there, 3 carbons. And so we can say that that's a propane, 3 carbons. First carbon is the alcohol 1, all. So starting with a primary halogenoalkane, we go through this intermediate, and we end up with this product. That's one type of halogenoalkane to look at. The extreme case on the other side is that if we take a look at one which is called a tertiary. So the tertiary halogenoalkane we're going to take a look at here in the second process. And this is a tertiary halogenoalkane. Okay? Why is it tertiary? If we take a look closely at the structure, we have notice here that this carbon, where the halogen is located, has no H's. And that's the definition of a tertiary halogenoalkane. Bring in the alcohol, notice again the OH group here, so this makes it the nucleophile. These electrons will bind. The final product is that this bromine will go away, this hydroxide group will bind in, and will generate this alcohol. So we're going from a tertiary halogenoalkane here to a tertiary alcohol. So again, we have to ask the same kind of question, and the question is, what do the reactions tell us? What do the kinetics tell us about this process? So we have this product. We take a look at the kinetics, and it turns out that in this reaction, the rate here, again, is dependent on K, the rate constant. But in this case, we find out that only the halogenoalkane here shows up as an important aspect. So we have to think about this. Remember that these guys here all are methyl groups. Here is our bromine. The hydroxide ion doesn't impact the rate at all. So how can we describe what's going on? Remember again, this is a nucleophile. Because it's attracted to the positive charge. So there's going to be a bond that's going to form between these 2 pieces. It is, again, a replacement, so it is a substitution reaction. So we're going to get the idea of S for substitution. It is a nucleophile, so we're going to get the N for nucleophilic. And it is a first order reaction over on this side, first order. So we talk about this as an SN1 mechanism. You might start to think about, why does it happen in this case that only this thing is important at first, whereas in the other one both took place. Start to think about the structure, arrangement of its shape, and that might help a little bit in that process. So as we come down here and take a look at this mechanism, let's think about what occurs. So here is our bromine. Apparently, according to our model, only this is going to make a difference initially in this first part. So how do we think about the process? There's a bromine. This bromine, this bond, is going to, they propose, break. Generate a Br minus and take the pair of electrons with it. So again, we're going to talk about a bond breaking. All the electrons go here. Terminology again is the idea it is heterolytic because it's not even. So it's a heterolytic break. Notice here that we've taken away this. This is a minus charge. So if we're taking the electrons all away from here, what happens on this side is that this is a plus charge. Plus charged structures are called cations. This is an organic cation, lots of carbons, so it's called a carbocation. This step, process, again is the slow step. We produced one of the products at this point, and this one, which again is not obviously going to be there, or not definitely going to be there, so we're going to call this a transition state. So it is speculative, but it does fit into the model that we have. So what happens in the next step? The next step, the fast step, this carbocation is now free to react with hydroxide. Nucleophile, negative charge. This pair of electrons, curly arrow, come in here, form a bond, this bond here, and form the alcohol. It's the carbocation plus the nucleophile in a fast step will generate the product. So the other product now here is our alcohol. It's a tertiary alcohol. Okay, so how do we justify that observation? Well, looking at this shape, note first the ion and notice the amount that's going on there. What we're going to propose is that a couple of things occur. One, because of these methyl groups that are here, because we had this structure, there is not sufficient space, so plus charge on it, for the hydroxide group to come in initially. So we're going to say that there is reason one, crowding. This is why it has to leave first. This is called steric hindrance. The other one is because of all of these different types of carbons that are here. You've got this carbon, and this carbon, being able to share the charge of this plus, that we can say that the extra carbon, number 2, can help stabilize carbocation, which means it has the ability to exist long enough so that it can exist and then react. And so this is the reason for the difference. So tertiary goes to an SN1 mechanism, primary to an SN2.